Okay, so we're going to talk about derivatives of general logarithmic and exponential functions, and we're also going to talk about this technique called logarithmic differentiation. So we already knew this, so you don't need to rewrite this down, but the derivative of natural log x is 1 over x. And we had already been working with this, which is if you have a derivative of a function, you have to use the chain rule. But with natural log, the derivative of natural log of a function, we use the chain rule. And the way that kind of manifests is if you're taking derivative of natural log of g of x, you end up with g prime over g. But again, that's review. We've covered that stuff and we've been using it throughout Unit 3. So just as a little warm-up, since we had a long weekend, go ahead and try and differentiate this situation using that rule. I'll give you about 2 minutes. All right, in the chat, what did we get? So you should just be using this rule that I circled in blue. Good. So, yeah, we should end up with just chain rule says derivative of the outside, which would normally be 1 over x, but in this case, it's going to end up just being 1 over what the input is, times derivative of the inside, which is 3x squared. So if we want to rewrite that, we have 3x squared over x cubed plus 1. All right, what about this one? Same idea. Derivative of natural log sine x ends up being 1 over sine x times cosine x, or cosine over sine, or cotangent x. Whoops, these aren't equivalent. I should not say that. That's the derivative. All right, so that's just some practice using the chain rule with natural log. A little more practice. If I wanted to differentiate this, I would have to use the chain rule, but now it's natural log as the inside function, right? So I would rewrite it as y equals natural log x to the 1/2 power. Now derivative of the outside, y prime, is going to be 1/2 times natural log x to the negative 1/2 times derivative of the inside, so times 1 over x. And then simplifying that, we'll end with 1 over 2x root natural log x. So it's this 2 and this x in the denominator, and then to make it a positive 1/2 power, I moved the natural log to the denominator, and then I just rewrote it as a square root. Okay, moving on. It's going to be shorter than I thought, I think. All right, so now let's talk about general logarithmic and exponential functions. So this is the new stuff. This is the party. All right, I'm going to come back to that slide, but I'm going to prove it to you first, and we're going to use a little implicit differentiation to do that. So let's just start with, let's say we have y equals log base b of x. And so I want to take the derivative of this. You have this thing called the change of base formula. You might remember it from pre-calculus. But change of base essentially just allows you to change any base logarithm to the base, any base that you want. And the way it works, whoops. So if we have y equals log base b of x, you can change the base to whatever you want. So I can change it to log base a of x divided by log base a of b. So that's the way the change of base formula works. But for us, the base that we're going to want to use is e, because then we can get this in terms of natural log. Remember that log base e is just natural log. So I can rewrite that as natural log x over natural log of b. And that's just the specific case where my base is base e, right? All right. With that in mind, another way of thinking of this is what I really have is 1 over natural log of b times natural log x. The thing I want you to recognize is that b is a constant. So this whole thing just represents a number. Okay? Natural log b is just a constant as well. So 1 over natural log b is also just a constant multiple, right? All right, so that when we differentiate that, you can just think of it as a coefficient, basically. And so all I really need to look at is the derivative of natural log x. What I end up with is y prime equals 1 over natural log b times 1 over x, which is 1 over x natural log b. And that's your formula for how to take the derivative of any general logarithm. So let's go back. Here you go. So write down that formula that's in the blue box. The derivative of log base b of x is just 1 over x times natural log b. The derivative of a general logarithmic function. All right, so this is log base 10 of 2 plus sine x. So we call this common log, log base 10. But we're still just going to have to use this formula to differentiate it. We're also going to be using the chain rule here, right? Because we're taking the derivative of the logarithm of a function, not just log base 10 of x. All right, so chain rule says derivative of the outer function, which is our log base 10. And that derivative is going to follow this rule, so it's going to be 1 over x natural log of whatever the base is. All right, so it's going to equal 1 over, instead of x, we're going to have just what our inside function is, 2 plus sine x, times natural log of the base, in this case it's base 10, so times natural log 10. And I'm going to multiply that by the derivative of the inside function, which would just be cosine, right? All right, and so let's just write that as 1 ratio cosine x over 2 plus sine x natural log 10. That's it. Not really much you can do to simplify that. Let's see, I think I put another one in here. Oh, no. All right, so here's your general formula for the derivative of an exponential function. And we'll go ahead and derive that. So the way we can derive that, I'm going to say y equals b to the x. So what I want to figure out is what's y prime, right? And the way we're going to do that is, remember, any exponential equation can be rewritten in logarithmic form. So I can rewrite this in an equivalent logarithmic form as log base b of y equals x. And then basically I'm going to do implicit differentiation here. So I'm going to take the derivative of both sides of this. Now, to do that, right, we want to replace y with f of x. So I'll have log base b of f of x equals x. And then I'll differentiate both sides. The right-hand side is just going to be 1. The left-hand side, I would use the chain rule. So it's going to be 1 over f of x, natural log of b, times f prime of x. Right, so this is the derivative of the outer function. Instead of x, I have f of x, and then I multiplied by the derivative of the inside function. All right, so now let's go back to terms of y. So I have 1 over y, natural log b, times y prime equals 1. All right, well, remember my goal is to figure out what y prime is, so I want to isolate that. So I'm going to multiply that y natural log b to the other side. So I have y prime equals y times natural log of b. But my original function is just a function of x, so I would like my derivative to also be in terms of x. So I need something I can replace y with. And we know that y is b to the x, so I can replace this y down here with b to the x. So this equals b to the x natural log b. And thus, I've proven that the derivative of b to the x is just b to the x times natural log b. Right, and that works with what we already knew, the derivative of e to the x to be. So let's think of that. Here, I'll do it in a different color. Because that should be, by this formula, e to the x times natural log of e. But in the chat, what is natural log of e? What does this evaluate to? Remember, when you evaluate a logarithm, you're thinking the base to what power equals the argument, and natural log is base e. So basically, e to what power gives you e? 1, right? Yeah, exactly. So that does, this just evaluates to 1, which means I have e to the x times 1, which is e to the x, which is what we knew the derivative of e to the x is, right? It's the special case where its derivative is itself. I don't think I put an explicit example in here, no. But here, let's go over, what if it was something else? Let's do like the derivative of 2 to the x would just be 2 to the x natural log 2, right? Or here, let's do one that's maybe a little more challenging. What if I ask for the derivative of 3 to the x squared plus 4? In that case, we're going to be using the chain rule, where the outside function is 3 to the x. So we would end with 3 to the x squared plus 4 natural log 3 times, then we would multiply by the derivative of the inside function, which is the exponent itself. So I would have times 2x. All right, any questions about that one? Okay, so logarithmic differentiation is a technique you can use to make taking the derivative of some kind of complicated functions a little bit easier on yourself. And we basically use it because the derivative of natural log is so nice, right? The derivative of natural log x is 1 over x, and even when it's natural log of a function, that's pretty easy to use as well, right? Because that just ends up being the derivative of the inside over the original inside function. And so we kind of use that along with properties of logarithms to make taking certain derivatives a little bit quicker. But to be able to do this, you need to remember 3 properties of logarithms, right? So I'll make a note of these here. And these basically derive, we already talked about these a little bit. I just want to remind you of them, but they derive because remember that logarithms are inverses of exponential functions. So these kind of come from properties of exponents that we already knew. But the first one is if you have natural log of a times b, that can be expanded to natural log a plus natural log b, right? The second one, same deal, but quotient can be expanded to the difference in logarithms. And the last is that if you have natural log a to a power of b, you can rewrite that where b is the coefficient of natural log a. And so we're going to use these 3 properties to expand and make taking derivatives of complicated functions a little bit easier. All right, and here are the steps. It's called logarithmic differentiation. So the first thing you're going to do is take natural log of both sides of an equation and use properties of logarithms to it says simplify. What they really mean is expand. Then we'll differentiate both sides with respect to x. Then we'll solve for y prime. Yeah. So this is the kind of case where you would want to use logarithmic differentiation. I don't know why it says example 9. It's like example 4 or something. All right, but you could do this. You could technically take the derivative of this directly, right? So just using rules that we already had. But you would have to do things like start with the quotient rule. And then within the quotient rule, you would be using product rule, chain rule again, and it would just get to be a huge mess, right? So instead, we're going to use logarithmic differentiation. It's going to make this much quicker and easier for us. And so the first thing we're going to do is take natural log on both sides. So we have natural log y equals natural log of, let's see, x to the 3/4 times, I'm going to rewrite that square root as an exponent while I'm here. So x squared plus 1 to the 1/2 over 3x plus 2 to the 5th. All right. So the next thing we're going to do is we're going to expand this using our properties of logarithms. So I'll do it in a couple steps, try and do it relatively slowly this first time, right? The left-hand side just stays as it is, natural log y. The first thing I'm going to do on the right-hand side is deal with this quotient, right? So remember, we had this property that said we have the quotient a over b, it can be expanded as natural log a minus natural log b. So that's all I'm going to do. So this becomes natural log of the numerator, which is x to the 3/4 times x squared plus 1 to the 1/2 minus natural log of the denominator. So natural log of 3x plus 2 to the 5th. All right, I'm going to keep expanding. So here, right, we have a product, and we had that property that said we could rewrite a product as a sum of logarithms. So that's exactly what I'm going to do. So natural log y equals natural log x to the 3/4 plus natural log x squared plus 1 to the 1/2 minus natural log 3x plus 2 to the 5th. And then last, we had that property that said what we could do when we had an exponent on our argument, right? We can bring that around as a coefficient on the front. So that's what I'm going to do here. All right, so we end up with natural log y equals 3/4 natural log x plus 1/2 natural log x squared plus 1 minus 5 natural log 3x plus 2. All right, so all this was just algebra. Now we're ready to do the calculus part, right? We want to find y prime. So we're going to use implicit differentiation. So we're going to differentiate both sides with respect to x. So on that left-hand side, when you take the derivative of natural log y with respect to x, you're going to end up with y prime over y. And that's just chain rule, right? Pretty much any time that you use this technique, logarithmic differentiation, that's what you should end up with on the left-hand side, y prime over y. So on the right-hand side, all of these are already written as functions of x, so we're just going to be taking the derivative of each logarithm separately. Remember the coefficient, this is just a constant multiple, so it just sticks around, it tags along, right? So derivative of natural log x is just 1 over x, so that first term just becomes 3 over 4x, right? Plus, the rest of these are logarithms of functions, so we are going to be using, I'm going to have to go way back, this idea here, right? So the derivative of natural log of a function of x, so derivative of natural log of g of x is g prime over g. All right. So this is going to be plus 1/2 times, again, we're going to do g prime over g. So it's going to be 2x over x squared plus 1. Minus 5 times, and this one's going to be 3. That's the derivative of the inside over just 3x plus 2. All right, so let's simplify where we can. This 2 in the denominator I can cancel there. All right, so let's go y prime over y equals 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. Right? But remember, my goal is to isolate y prime, so I'm going to multiply this y to the other side. So I'm going to end up with y prime equals, what do I have here? 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2 times y. And last, my original function is just in terms of x, so I would like my derivative to only be in terms of x as well. So I need to be able to replace y with something, which I can right here, right? This is what y is. So yes, this comes out to be an ugly monstrosity of a function. That's okay. 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2 times x to the 3/4 root x squared plus 1 over 3x plus 2. There you go, final answer. Yeah, it's nasty looking, but it's much more straightforward to use this technique, so to take natural log of both sides and then differentiate, than it would have been to just try and directly differentiate and have to use like 5 rules to do it.